We'll get started. So we were talking about stability of the nonlinear systems in the previous class. So we had x dot t equals to axt plus fxt. A is Hurwitz. What that means is real part of lambda IA is less than 0 for all I, and f of x small o of norm of x as norm of x goes to 0. And what we had said was, if this condition is satisfied, then there is a delta ball around 0 such that x is exponentially stable within that ball. So here is my x equals to 0. Here is a region where system is stable. In fact, it's exponentially stable. And if you start from here, then the trajectory might go to infinity. It could go anywhere. It could go to infinity. It could go to origin. But certainly around 0, the system is exponentially stable. And I wanted to show you a few examples of systems of this type. So let's say my x dot t, so examples. I don't like this chalk. X dot t equals to minus xt plus 1.5. X dot t equals to minus xt minus 1.5. So let's look at these three systems. No, these four systems. Which of these are going to be exponentially stable? Do they meet the criteria that we have laid out here for the system to be stable? Which of these are stable? We have system 1, 2, 3, 4. Any thoughts on which of these are stable, which of these are unstable?
The third one is only stable.
Sorry?
Isn't the third one always stable?
Right. So it turns out that all of them are exponentially stable around 0 because it meets this criteria. So A is Hurwitz. So if you look at the A matrix here, it's -1. So the real part of eigenvalue is strictly negative. And if you look at f of x, which is the second term, the nonlinear term, these are the nonlinear terms. They are of the order of norm of x, small o of x as x goes to 0. So as x goes to 0, these are all of the order of norm of x. But let's do a somewhat of a heuristic. Let's do something which is a bit heuristic to try and understand what is this radius in which this is going to be exponentially stable. So what happens when xt is less than 0. It's less than 1. So this term is going to be smaller than x of t, right? So this term, because this is x of t raised to 1.5. Let me add another system. X dot t equals to minus xt plus square root of absolute value of xt. Okay, so this is unstable. This is not stable. Or I actually shouldn't say it's not stable. Uh, well, it will turn out that it is not stable. But right now, we don't know whether this is stable or not. It doesn't fit into this criteria. So A is Hurwitz, but this term is not small o of x. Remember, what I said was that for small o of x, it should be xt norm raised to 1.1 plus epsilon. So these are all 1 plus epsilon type behavior. So therefore, they will fit this particular criteria. This one is not going to fit the criteria. So here f of x is not O of norm of x. Okay. So going back to our heuristic discussion, so if xt is close to 0.999, this term is smaller, this term is bigger with a negative sign. So the overall term is going to be negative. So x dot t will have a direction which is towards the origin. So that's going to be the case here. What about when xt is close to -1? Then this one is positive. This one is small but positive, so it will still be pointing towards the origin. So in all of these cases, if you can imagine, we will have the situation where every time you are within the unit circle, your direction is going to be pointing towards the origin. What happens if you're outside of the unit circle? What happens if xt is greater than 1? If xt is greater than 1, where is this x dot t pointing towards?
You.
Yeah.
So I guess if you're greater than one, you would go towards infinity, right?
Right. So this one is dominating this particular term. So this one is trying to push it towards origin, but this one is trying to pull it away from the origin. And as a result of which, this is going to be dominating because xt is greater than 1. So x dot t is pointing towards infinity. What about in this case?
In that case, it should be globally exponentially stable, right?
It will be globally exponentially stable, but how would you prove that this is globally exponentially stable? You are absolutely right. Your intuition is correct, but how would we prove that this is globally? So all we have done is change the sign here, but this one is unstable outside of unit circle and it's stable inside the unit circle. This one is globally stable, but how do we prove that this is globally stable? I mean, certainly it fits the criteria here, so that tells you local stability. It doesn't give you global stability.
I would just use a Lyapunov function.
Wonderful. Lyapunov function. Okay, so let's say v of x equals to, what's your favorite Lyapunov function?
Just x squared.
Just x square. Yeah. You are as boring as it gets. So what is v dot of d over dt of v of xt? We are looking at system 2. So we are looking at system 2 here. This is 2x minus x minus 1.5 square root of norm of x. This should be actually functions of t. So what do I have here? Minus 2xt square minus 3 Is it strictly negative everywhere? I think it requires a little bit of work, but I'm inclined to believe that it will be for xt greater than 1. So for xt less than 1, this is stable, as we had pointed out. For xt greater than 1, this term is going to dominate this particular term. No, it will not. Actually, it will not dominate. So we don't know whether it's globally exponentially stable or not. Maybe I'll have to take some other Lyapunov function, some other carefully constructed Lyapunov function.
Well, yeah, because I didn't think about the absolute value.
Yeah.
That.
Right. So I don't know whether it's globally exponentially stable or not. We can definitely do simulations to figure this out. Maybe that's a good assignment problem. But yeah, the Lyapunov is not giving me any conclusive answer, but that's because I've picked the Lyapunov function, which is very simple. And around 1, this is going to be -2. Around -1, this is going to be -2, but this is going to be +3 multiplied by square root of 1. So that's going to be +3. So for some reason, around -1, the Lyapunov function is going up. The time derivative is positive, so I'm not quite sure what the stability property looks like. But certainly around origin, this seems to be stable. Let's look at number 3. What about number 3? So inconclusive. So this is stable in unit circle. This is stable in unit circle. Probably this is also stable in the positive half plane. So if xt is positive, this is stable. Xt is negative, we don't know what the system is going to look like xt less than -1. I don't know what the stability properties are going to look like. For this particular thing, system number 3, what do you think? Naturally, it's also stable in the unit circle because of the theorem we talked about in the previous lecture, that is theorem 4.32. I had mentioned this theorem in the previous lecture, so I'm just recalling that from that lecture. Okay, going back to number 3, what do you think? Is it globally stable, locally stable? All I have to do for number 3 is so what do I get? -2 x raised to 4t. This is strictly less than 0 for all xt greater than for all xt not equal to 0. So this is actually globally stable. And this is also stable at unit circle. Okay, and this one is not going to be stable because it doesn't meet this criteria. It doesn't meet the criteria of fx being small o of x. Okay, so to some extent, we now have a tool that tells us about local stability property of nonlinear system, as long as the nonlinear system can be written in this particular form, and the nonlinearity is small o of x. Okay, so it should have 1.5 in the or 1.01 in the exponent, but it cannot be square root or xt raised to 0.99. So here is what I'm going to ask you to do in the assignment. I'm going to ask you to simulate the trajectory of this and the trajectory of 0.99. I'm going to write down the assignment today, which is I'm going to ask you to simulate this trajectory and simulate this trajectory and see what kind of behavior you see, the stability behavior you see in the system. So my hunch is this one is going to be stable because of this theorem, and this one is going to be unstable because of the discussion we just had in the classroom. For some initial condition, it will be unstable. Okay. So what does the proof say in this case? I'm going to pick the Lyapunov function. I'm going to give you the outline of the proof. X transpose Px. So my V dot of xt is xt transpose G xt plus 2x T transpose P fx. And remember, G was negative. Because A is Hurwitz, I can show that G is going to be negative. P is positive definite, P is greater than 0, and G is negative definite, G is less than 0. Okay, so now here is what the proof is. This one behaves like O of norm of x, O of norm of x, and this one behaves like negative norm of x square. So you are adding something which is negative norm of x square with something where you have x multiplied by small o of x, norm of x. So overall, this term is going to be negative close to origin. So if x is less than epsilon, then this term is going to be, or x is less than delta, then this term is going to be less than 0. As a result of which, the system is going to be stable within that ball, delta ball, around 0. And in all these cases, the delta ball was equal to 1, the delta was equal to 1. But depending on what the coefficients are, you could have different values of delta within which this system is going to be exponentially stable. Okay, this is a very, very typical proof technique in the context of, well, not just dynamical systems, but also in optimization and in reinforcement learning and so on. You make some assumptions on the system so that this term is dominated by something that is negative of the norm square, and as a result of which the overall Lyapunov function becomes less than 0 within a certain delta ball. In the context of dynamical system, general dynamical system, this delta ball around the origin is called the basin of attraction. It's called a basin of attraction because any trajectory within that particular delta ball converges to 0 exponentially fast. Okay, basin of attraction, that's the keyword. Any questions so far? Okay, the proof with all the epsilon and deltas are given in the book. So I encourage you to read the book if you're interested in knowing the precise proof for this particular result. Wonderful. So what we have done so far is talked about stability of linear system. This is the internal stability of the system. So we are looking at the stability of the entire state space. And we are talking about under what condition is origin going to be a stable point, exponentially stable point, or just a stable point for the entire system. Uh, but in many cases, we don't quite see the entire state space. We are just seeing some part of the state space. And therefore, we are interested in the input output stability of the system. So, to give you an example, suppose I have blood pressure and I'm taking a medicine. So, medicine is the input. That's what I'm eating. That's the input to the body. And the output is my blood pressure, which is what I'm observing. I'm not observing everything else that the medicine might be doing within my body. So it might be going in my gut, it might be reacting with hydrochloric acid, then it might be going to the pancreas, the intestines, then it will get absorbed in the intestine, it will go into my blood vessels, then it will go to appropriate location within heart and figure out what the optimal blood pressure for my body is going to look like. And so when I start running, when I start climbing stairs, it's going to figure out what's the appropriate amount of blood that needs to be pumped to my legs and to my rest of the body in order to meet that requirement. So I'm not looking at everything that's happening inside the body. There's no way that nobody, even the advanced equipments that we have at our disposal, cannot measure where that drug is going and what cells it is interacting with, what's the interaction mechanism at the molecular level, and figuring out that this is exactly the process through which my blood pressure is getting controlled by the medicine. Okay, so that's a situation where we cannot measure. There is just no way to understand the internal stability of the system. So if we don't know what the internal stability of the system is, all we can see is input output stability. So if I give it a bounded input, I see a bounded output. That's all I can measure, that's all I can see. And so let's talk about bounded input, bounded output stability for systems that are partially observed. I have x dot t equals to axt plus but. I have yt equals to cxt plus dut. So it is desired that bounded input should lead to bounded output. That's what BIBO stands for, bounded input, bounded output. Definition. System is BIBO stable if and only if x0 equals to 0 ut is less than 1 for all t, t greater than equal to 0, then there exists c greater than 0 such that yt is less than equal to c for all t greater than equal to 0. This is L2 norm. We are talking about L2 norm here. So just something to keep in mind. It doesn't matter which norm we are picking. It could be L infinity norm or whatever norm you want to pick. L2 norm is just easier to work with. Okay. Let's look at the impulse response of the system. Well, the first note that I wanted to make is, if we are looking at the norm of yt, I know that the norm of ut is less than equal to 1. That's what I have written here. So the norm of ut is less than equal to 1. This is a finite matrix. So all I have to care about, so even if I prove the result for d not equal to 0, the result will automatically get proven for d equal to, sorry, even if I prove the result for d equals to 0, if your d is non-zero, you can come up with a different c prime that satisfies the criteria for the case with d. So I'm going to set d equals to 0 for now. What is the impulse response? C e raised to at b this is ht, and so the system xt is given by e raised to at x naught plus integral 0 to t ht minus tau u tau d tau. Oh, this is not xt, this is actually yt. Yeah, this is correct. Okay, so if you give the system an impulse at time t equals to 0, this is what the output is going to look like, and so that's given by the impulse response matrix. So that's what is going to give you the impulse response matrix, and then you do this convolution between the input and the impulse response matrix, you get the output of the system. Okay, and this is the input output relationship. Remember that in this particular system, I cannot open the system and look what's happening inside. All I can do is observe the output. I have a sensor, I have a temperature sensor of the room, and I can measure the temperature of the room. But I cannot put a sensor all over the room to figure out what the average temperature of the entire room is. All I have is one temperature sensor in the back of the room. And so this area of the room can get cold. No, that area can get cold because you have a vent outside, vent right above you, but that area of the room may not get cold. But the temperature sensor will only measure the temperature of that particular area. It doesn't have any information about what the temperature of this area in the room is. And so in Dree's lab, for instance, at every floor in the summer, you have a different temperature. So you want to enjoy Florida, you go down. You want to enjoy Antarctica, you go up on the 7th floor. And you can get like the entire world's temperature within the same building. But that's only in the peak summer. Okay. Uh, Wonderful. So this is the definition of BIBO stability, that I start with zero input. So this particular term is zero. Zero initial condition. So this term is zero. I am giving it an input which is strictly less than one for, less than equal to one for all time t greater than equal to zero. I want the output to be bounded at all times. Okay. And the theorem in the book is theorem 4.37. System is BIBO stable if and only if supremo over t greater than equal to 0 So this is the matrix norm. This one is a matrix norm. You can pick the two norm. So I take the matrix norm and I integrate from 0 to t, and that has to be bounded. It has to be less than equal to L for all time t greater than equal to 0. This L is a finite number. Okay, let's try to prove this result. System is BIBO stable, so then this must be true. Let's say my ut less than equal to 1 for all t greater than equal to 0. So I have yt Oh, this is the other way, I think. If that's the case, then system is BIBO stable. So this is the other way. And so this is less than equal to L, which is less than infinity. So this implies BIBO stable. Why should this inequality be true? Yes, please. You are kind of right.
It's not exactly triangle.
It's not quite triangle inequality, but you are kind of sort of right. So you can think of this integral as summation of the matrix multiplication multiplied by delta t, and you can sort of break it up into a summation. And so the norm of the summation is less than equal to the sum of the norm. And then you can take limit on both the sides and you get this inequality. Okay. So it does follow from triangle inequality, but there is a bunch of steps involved in the middle. Okay, so absolute value of an integral is less than equal to the integral of the absolute value. So that follows from the triangle inequality, but it does require a proof, but I'm not going to prove that in this class. It's a topic in measure theory, but not in this class. Okay, so we get this. Now I know that u tau is less than equal to 1 from assumption. So I get that. I take it less than equal to 1, so I get this inequality here. So I have this matrix norm. Now I know from the assumption that this particular part is less than equal to L. So it's less than equal to L. So this implies BIBO stability. So that part is straightforward. The reverse implication. Now let's look at the forward implication, which is if system is BIBO stable, then this must be true. How would we go about proving it? So if the system is BIBO stable, if the system satisfies this condition, then this statement must hold true. Is it obvious? No, it's not obvious actually. But how do we go about proving it? It's a bit complicated. Yeah, you have an idea?
If at any point at ht minus tau is like infinity, it would go to infinity, but yeah, that's why I thought for all this.
Right. So you are on the right track, but then you are proving the contrapositive statement, and that's what I wanted to make sure that the class understands. So we want to prove the reverse implication. Any questions on this before I erase this side? Okay. So I want to prove the converse, which is this part, which says that if system is BIBO stable, then this implies that sup t greater than equal to 0, this integral is less than equal to L. That's what I want to prove, but that statement is very difficult to prove. So I'm going to take the contrapositive statement. Which is if my supremum t greater than equal to 0, this integral is there's no point writing that it's equal to infinity, so I'm going to write it in some other way. There exists for every L, there exists TL such that integral of 0 to TL norm of h TL minus tau d tau is greater than L, then not BIBO stable. So this statement is negation of this particular statement, and this statement is negation of this particular statement. Okay, and that's called a contrapositive statement. So proving this is equivalent to proving the contrapositive statement. Now what do I do? Okay, so this appears to be a very difficult problem. So let's try to figure out how to solve this problem. So I have this matrix norm integral greater than L. What does that imply? So this matrix norm, for every L greater than 0, I can find a time t such that this particular norm is greater than L. This is a matrix norm. So there must be one element of the matrix, at least one element of the matrix that's going to infinity. At least one. Okay, there could be more, but there is at least one element. So let's say H Ji is one such element. This should be TL. Oh yeah, this is TL actually. Hji TL minus tau d tau is greater than equal to L over MP. So this is the jth observation. So this is Yj and Ui. So this is the transfer function, or this is the impulse response. If you put an impulse input at time 0, Ui is an impulse input at time 0, and you're observing only the Yjth channel. So you have two drugs for controlling the fever, and you give one drug and you're looking at the temperature of the body. That's the output that you are observing. You don't know what's happening inside the body. I have no idea what's happening inside the body. I gave the drug, the ith drug, and I'm looking at the jth output of the system. Okay, so that makes it a simple statement. So now this particular jith term is actually going to infinity as t goes to infinity. So what I'm going to do is I'm going to define my ui of t as follows. It's going to be plus 1 if h ij t minus tau is greater than 0. It's going to be 0 if h ij t minus tau is equal to 0, and negative 1 if this is less than 0. This is another very classic, yeah.
What is L over MP?
M is the dimension of U. So U is in Rm and Y is in Rp. Okay. So if a bunch of sum is greater than L, so remember this is a bunch of different elements. If that is greater than L, then there must be one term which must be greater than L over MP, because each of the term is positive. Good question. And then, yes.
Why is it HJI and HIJ?
Oh, HJI. Yeah. So jth output, ith input. Thank you so much. This should be HJI. T minus star. Yeah, perfect. This one is good. So now I get that. I have constructed a U, a specific U based on this impulse response between the ith input and jth output. I have constructed an input signal in this particular fashion. One thing you will notice is that this input signal is always at the boundary. So remember, I have written ut has to be less than equal to 1. I have constructed a u signal which is on the boundary at all points of time. It's either +1 or -1. The 0 thing you can kind of ignore because this transfer function itself is 0, or sorry, the impulse response matrix component is 0. So it doesn't matter what value of u you pick. But other than that, you can pick this, and then you can show that with this particular UIT, your YJTL is greater than equal to L over M rho. Sorry, MP. So not BIBO stable. You have a question? No? Okay. So I wanted to introduce two new techniques for your benefit. One is this proof by contrapositive statement. This is what I wanted to prove. I don't know how to prove it. So I come up with a contrapositive statement. Now, contrapositive statement is much easier to prove. So I start with this contrapositive, I start with the hypothesis of the contrapositive statement, and then I construct a very specific U which shows that Yj is unbounded. So for every L greater than 0, I can find a TL such that Yj is greater than equal to L over MP. This part is a constant, so I can forget about it. But I can let the L go to infinity because this is true for every L greater than 0. I can let L go to infinity, and I'll find that Yj will also go to infinity. So that's the reason why. So that's how you essentially end up proving results of this particular type. If you started with BIBO stability and you wanted to prove this, it's probably impossible to prove it, because starting with this definition, I don't think I can prove this this implication. But starting from this hypothesis, I can definitely prove this. Okay. Any questions so far? Any heartaches? Okay. Perfect. So we have finished chapter 4 with this. And now we are moving on to chapter 5, which is about reachability and controllability. It also talks about observability. So I'm not going to talk about observability today itself, even though in the chapter, so I'm going to mix the chapter a little bit. So in the chapter, it talks about controllability, observability, and then theorems. I'm going to talk about controllability and the theorems first, and then I'll talk about observability and the theorems. Okay, so what's the situation with reachability? So reachability, a system, okay, so let's think from a robotics perspective. I have a robot, I want it to go and maybe pick an item. So the robot has to take a sequence of control actions in order to get to the item and pick it up. Okay. So it has to, every element of the robot has to be in a specific orientation to be able to do that. Right? So that idea is studied under the umbrella of reachability. So I'm starting from 0 position. So my initial state is 0. I want to get to a specific state. Can I get there? So the question right now is just, can I do that? I have a car. I want the car to accelerate from 0 miles per hour to 70 miles per hour in 2.6 seconds. Can I do that? Is it possible to do it with this particular vehicle that I have? Okay, so why is this important? Why is this car example important? Well, Tesla does that, right? That's in their marketing brochure, that some of their higher end cars, they charge $80,000, $90,000 for that car. But the claim to fame for that car is it goes from 0 to 60 miles per hour in 2.6 or 2.8 seconds. Okay, so that's the reachability question. Can I reach? I'm at rest, or I may be waiting to merge into the highway. I have to go from 0 miles per hour to 70 miles per hour or 60 miles per hour, and I want to do it in as small time as possible. So if you buy a very basic car, a $20,000 car, you probably will do it in 8 seconds or 9 seconds. You can go from 0 to 60 miles per hour. But in Tesla, you can do it in higher end models of Tesla, you can do it in 2.6 seconds. So that's a reachability question. Can I go from one state, 0 state, to some other state? The reverse question is a controllability question. I'm at 60 miles an hour. I saw a trash bag or a deer in front of me. Can I stop my vehicle in 2.6 seconds? Okay, that's the controllability question. So reachability, so in a car, so let's go back to this car example. So what allows a car to go from 0 to 60 miles per hour in 2.6 seconds or 2.8 seconds? I don't know what the number is, but I'm assuming it's somewhere in 2.6 to 2.8. What makes it go from 0 to 60 miles an hour in 2.6 seconds? Any ideas? Yes.
Like the efficiency of power, the energy of
Efficiency of, I don't think it is probably the efficiency problem of converting the energy, maybe like whatever the battery is doing, into torque. Maybe not the efficiency. I don't know what you mean by efficiency, but definitely the power electronics should be able to produce so much current that can go through the motor, that can provide so much torque.
That's what I meant actually.
Yeah. So that maybe efficiency is not the right word for it, but yeah, I understand what you mean now. But that's not enough. Okay, your tires also have to be really good, because tires are the one that's converting the torque into propulsion motion on the vehicle itself. Okay, so the tires have to be high end, and the friction coefficient of the road also has to be pretty good. Okay, so if it is raining, if it is snowing, you probably won't be able to do that. Awesome. What about the controllability question? I'm driving my vehicle. There is a deer right in front of me. I just spotted the deer right in front of me, and I need to stop the car within 2.6 seconds or whatever, 2 seconds. What allows you to stop the car in 2 seconds? Any thoughts? So you go from 60, 70 miles an hour to 0 miles an hour. Yes.
You have to make some brakes and the engine if you downshift.
Right. Okay. So there is braking because of the you can regenerate the energy, so that's braking motion from the motor slash so from the motor itself. You also have the actual brakes on the vehicle, so that's also helping. And then the third thing, which is again the friction coefficient between the tire and the road. So those are the three things that makes the vehicle stop within 2 seconds. So you go from 60 miles or 70 miles an hour to 0 miles an hour. Okay, so that's the reachability and observability question. And the way we define reachability is as follows. XF is reach, so XF in Rn is reachable if and only if there exists capital T greater than 0 and u from R to Rm such that x0 equals to 0 and xt equals to xf. This is the definition, that's why I'm writing it as if and only if. I want to remind you that my equation of motion is the following. Okay. So xf is reachable. So I want at time capital T, I want to reach xf. I don't care what that capital T is. That capital T could be 10 seconds, it could be 100 seconds, it could be 1 million seconds. Okay, so somehow the Tesla example is not embedded here, but at least you got the idea. So there exists a time t greater than 0 such that I can reach that particular final state xf. So there exists a t greater than 0 and a sequence of actions, a time series, or a function u, which is a function of time, maps to Rm. Naturally, the u has to be equal to 0 for t less than 0. So for time t less than 0, you're not really applying any action. But at t equals to 0 to t equals to capital T, you are actually applying some action in order to go from state 0 to a final configuration. So in robotics, this final state is known as a configuration. In controls, you call it a state, but you understand the idea. You want to reach a specific configuration or a specific state, and it doesn't matter what time, how much time it takes for you to reach that particular action. But your system is capable of reaching that particular location in the state space. Yes, please.
Is state reachability defined for the x0 equals 0, or can we define it as also x0 equals 1 or something else?
A very good question. So reachability is defined always from 0 to a specific state, and controllability is defined from x0 to 0. And so if a system is both reachable and controllable, you can, let's say you want to go from you want to go from x0 to xf, you spend capital T time step to get to 0, and then you spend another capital T time step to get to xf. Okay, so you can still go from one point to another, but naturally in real systems you have much better algorithms to get you from one state to another state. Okay. Any question? Any other question? Okay.
Um,
Yes.
So
would we consider reachability in natural response of system, like which is not being driven by input?
No, then you're not really reachable. You are just the response, the whatever the impulse response is or whatever the input is, it just naturally parsing within the system, but you're not really, the system is not intending to go to a specific state. So the reachability and controllability is way more important in the robotics. So I don't know if you've seen some of the latest robotics video, but let's say a robot is jumping or is dancing or whatever. So what all things robot can do, what way it can dance, those are all sort of under the umbrella of reachability. Okay. Awesome. Let's look at an example. So I have, let's say my B matrix. So A has eigenvalue lambda. So A has eigenvalue lambda and vector, corresponding vector V. And let me define my B as V. So I stack the vector, the eigenvector of A matrix as my B matrix. Let's look at what all states this particular matrix is going to visit. What's my x of t? So my x0 equals to 0. Okay, so my x0 equals to 0. So this is integral 0 to t e raised to a t minus tau. This is tau. So this is 0 to t e raised to a t minus tau v u tau d tau. What is this term? Can someone do the calculation and tell me what this term looks like? U is a scalar here, so ut is just in. Yeah, you have.
Well, I mean, I don't necessarily know exactly what that is, but those be like the modes of the robot, so like its joints. So it'd be like, I don't know if that makes sense necessarily, right? But it'd be like,
Yeah,
how it moves in its different coordinate system or something.
I mean that's what this xt is giving you, like in the different coordinates, what exactly are the coordinates that is visited by that particular robot. But this expression has a very simple outcome, like it can simplify quite a bit, and I just want you to think about it and tell me what this expression looks like. I mean, what should this be equal to? Just write the matrix exponential expression multiplied by v and you will get something. Remember, v is an eigenvector, so av equals to lambda v. Any idea? What is e raised to a t minus tau times v? So this is a matrix, this is a vector. I'm multiplying a matrix by a vector. What is that new vector going to be? Okay, so this is going in your quiz 3. This is e raised to lambda t minus tau v. Okay, if you write the expression for matrix exponential and you multiply it by the matrix V, because of this identity, you will see that this is e raised to lambda t minus tau times V. Okay, so if this is equal to this, then what I have here is 0 to t e raised to lambda t minus tau u tau d tau. This gets multiplied by V. Because this is a scalar now. This is a scalar. And this is also a scalar. Okay, so what I get is that xt equals to some scalar times V. So what's the reachable set from origin? Where can I reach from the origin? That's right, eigenvector. The vector space corresponding to the eigenvector. So you can only, so in this case, the reachable set span of V. This is my phase space. x1t, x2t. This is V, and I can only reach the points along this particular subspace. I cannot go to any other. If I want to reach here, I cannot do that in this system. So this point is not reachable. Okay, so there is a, so in parallel parking, right? So when you have to park parallelly, your initial state is you're standing here, your final state is you have to stand here, and then there is a very complicated trajectory that you have to take in order to get to the spot. Just go 1 meters on this side. It takes quite a bit of effort. Okay, but you still can do it. Given enough time, you will be able to reach that particular state. Awesome. So in this particular system, when B is comprising of the eigenvector of the A matrix, the subspace generated by that V, only that particular subspace is reachable. Everything else in the space is not reachable. Okay. So now the question is, under what conditions can I reach any other point in the space? And global reachability, which is trying to be, I mean, getting to a point anywhere in the space, is actually a very important problem. In general purpose robotics, it may not necessarily be a problem if you are building a robot for manufacturing vehicles, because that only has to do the same thing again and again, right? So in manufacturing, the robot doesn't have to reach anywhere in the state space. It just has to do the job it is designed to do. But if you have a general purpose robot and you want that robot to also load your dishwasher, clean your laundry, iron your clothes, um, clean up your house, run vacuum cleaner or whatever, if you want the robot to be able to do everything, then it has to be globally reachable. So there are reasons to have globally reachable systems, and there are reasons to have limited reachability system. And so so it's important to characterize under what conditions a system is reachable. Perfect. So in order to study that, in order to understand reachability, I have to give you a few more definitions. And then maybe I'll do the proofs in the next class. So I've talked about state reachability, state controllability. Let me reachable subspace. Set of all reachable points. The book denotes it by RR, and completely state so set of all reachable points is denoted by RR. So in our case, in the case that we just talked about, the RR was span of V. The set of all reachable points was span of V. V is the eigenvector, and the completely state reachable, I would have named it globally reachable, but for whatever reason, the author has written completely state reachable. But yeah, we'll go by the author's, whatever name the author has given to this property. I'm going to define controllability matrix. It's denoted by C. So this is script C, this is mathcal C, and this is given by B, AB, A raised to n minus 1B. Remember, n is the dimension of X. And this is a matrix in Rn cross Mn. This is M columns, this is M columns, this is M columns. And the last thing, reachability Gramian. I want to make a note here, which is pretty unfortunate. So this T is transpose and this T is time, capital T time. This is B transpose, this is A transpose, and this capital T is this capital T. This is time. Okay. The other one, the other result that I want to remind you, I mean, maybe not remind you, you probably have not studied it before, is Cayley-Hamilton theorem. Which says that let P lambda be determinant A minus lambda I equals to beta 0 plus beta 1 lambda plus beta n lambda raised to n. So Cayley-Hamilton theorem is A.27. So theorem A.27. It's in the appendix. A in R n cross n. Then PA equals to 0. So this is the polynomial in lambda. I'm going to replace this lambda with the matrix A. And I get a 0 matrix. This PA is 0 n cross n, which is beta naught I plus beta 1A beta n A raised to n. This is Cayley-Hamilton theorem, that every matrix A, square matrix A, satisfies its characteristic equation. This is the 0 matrix, and you replace 1 by identity, lambda by A, lambda raised to n by A raised to n. That gives you the value of P of A. And so every square matrix satisfies its characteristic equation. This is the characteristic equation of A. Perfect. So I think we have all the tools needed to understand reachability of a system. We are going to talk about under what conditions is a system globally reachable. And the idea there is that if controllability matrix is full rank, then, so full rank means it has to be rank n, because it is, m can be greater than equal to 1. So this is definitely, n is the smaller of the two dimensions. So if it is rank n, if the controllability matrix is rank n, then the system is globally reachable. Okay, and it will turn out that if it is rank n, then it's also globally controllable. Perfect. Oh, I'm using globally, but what I actually mean is completely state reachable. Okay. Any questions so far? Awesome. So in the next class is going to be, we'll use the controllability matrix, we'll use the reachability Gramian, we'll construct this control strategy, control policy U, such that xt becomes equal to xf, and then we'll talk about the complete state reachability, and in order to prove the result, we will need this particular statement, Cayley-Hamilton theorem. Perfect. I'll see you on Tuesday next week. Have a great weekend. Thank you.